So yesterday we saw how to derive from first principles the most basic amplitude, which is a 3-point amplitude, and there were two, actually let me write out the indices as well. And again, the convention is that the indices here, the numbers, represent that index into the external set of external momenta, so this would be K1. And we derived on first principles this amplitude and also the conjugate amplitude. And we saw that if all the helicities were equal, the amplitude vanished. We also saw that if we wanted to turn this into a complete amplitude, not just a color-ordered amplitude, then we needed to dress this, and I'll put in the factor of the coupling. I'm usually going to omit the coupling. We have a color structure, and then it's a 3, 1, 2, 3. So at tree level, we can just determine the number of powers of the coupling from the number of external legs. It just generalizes what we see here. If we have an n-point amplitude, then we'll have a g to the n minus 2. And so I'm just not going to bother writing it. I'm just going to leave it implicit. Now, I promised that from this very modest object, we're going to be able to compute everything. And that you can imagine that means we're going to have to sew these amplitudes together, in which we'll see very shortly what that means. But before we start talking about sewing together the kinematics, we should talk about sewing together the color degrees of freedom and how the color degrees of freedom organize themselves. Now, I know that Henrik has already talked about this yesterday, but I think the way I'm going to present it is a little bit different, and so you'll have two different views on how one can organize this. So you can imagine that the thing that sews together two different 3-point amplitudes, for example, into a 4-point amplitude is going to be it's essentially going to be the identity in color space, so it can look like some sort of Kronecker delta, where the x and y legs are being sewn together. And so then the 4-point amplitude is going to look something like this. So we're going to have 1, 2, and x is some leg that's going to be sewn together. There's going to be an f, a1, a2, ax. And then we have a delta. And then we have ay, a3, a4, and another 3-point amplitude y, 3, 4. So the structure constants we can write in terms of traces of generators in the fundamental representation, and the normalization here may be a little bit different than what you're used to. There are a variety of conventions. The normalization that I'm following here is where the trace is normalized to just be delta AB, and that means you don't have to shuffle around lots of powers of 2 between different places. So this is actually the sensible one. If you look at older physics literature, that's not the one you'll find, and I think in some of the math literature, you also have a different normalization. So we're going to need to use a Firth identity in order to do this sewing together. And we're usually interested in SUN theory. And in particular, for collider applications, we're interested in n=3, which is quantum chromodynamics, or QCD, the theory of the strong interactions. But for our immediate purposes, it's actually going to be easier to think about UN, which at the algebraic level is just SUN cross U1, because it makes the sums that we're going to do simpler. So as long as we're not thinking about matter's degrees of freedom, so in the context of QCD that would be quarks, then in fact, as long as we don't have any degrees of freedom that are transforming under representations other than the adjoint of the group, then the full amplitudes for these two different gauge groups are going to be the same, because the U1 is simply not going to interact. The photon is going to be inert. So in UN, the Firth identity is very simple, just taking the form. So it's something where we're summing over the Lie algebra indices, and we're leaving the actual representation indices free. So we have the first one indexed by 1 and the second one by 2. And so this thing is just going to be, it's essentially just exchanging the indices. And in SUN, there would be an extra term, which you can actually work out for yourselves. And so now if we want to contract our two structure constants, then we can write that out over here. We just have two traces, A1, the commutator of A1 and A2. And then the commutator, and I'm using the cyclicity of the trace here to rewrite this in a more obvious form. And so this thing is just going to give us, it's going to combine the two traces together. So we get a sum over single traces. And as we sew on more and more 3-point amplitudes, we can iterate this. And so that means that for the full endpoint amplitude in pure Yang-Mills, we can write, and again, the calligraphic symbol is representing the full amplitude, so this thing will depend on the spinors. It will also depend on the helicities of the external gluons, and it will depend on the color indices. So this thing is going to be a sum over permutations, and I'll explain the notation in a minute. So these are this is, well, let me write it out first, actually. So, and again, I'm dropping the factors of the coupling. So we have a single trace with the indices arranged according to the permutation, and that is multiplied by a color-ordered amplitude. And here I'm just going to write out the, I don't know how legible that's going to be. I'm just going to write out the indices, the helicity index I'm leaving implicit over here. So this is our color-ordered amplitude. And the Sn here is the set of full permutations of n objects. And we mod out by the cyclic permutations represented by Zn. And that corresponds to the fact that there's a cyclic invariance of the trace. And so we would be multiple counting. I mean, you could multiple count and just divide by the normalization, but it's easier just to remove them from the very start. And in the case where you do have matter fields, then the structures will be different. So for example, if you have matter fields that transform in the fundamental, like quarks, then you'll have to have indices corresponding to those quarks. So you'll be removing the traces and attaching the indices to a string of representation matrices. These matrices here are understood to be in the fundamental representation of the gauge group. So we're mostly going to be focused on studying the kinematic object. So this object is going to be the same independent of n. In fact, it would be the same even if we had an SON gauge group as well. And in order for this kind of sum to make sense, or in order, then it has to match the same symmetries as the trace would have. And so there are two symmetries which I think, again, Henrik has already mentioned. So first of all, they should be the ANs should be symmetric under cyclic transformations of the arguments. And there's also a reflection identity, so that AN of, if we reverse the order of arguments, there's a sign depending on whether n is even or odd, and then it's equal to the amplitude with the original set of arguments. Now, we started out by doing this in UN, but as I'd already mentioned, the U1 doesn't couple. So implicitly, I'm assuming here, in order to get something non-vanishing, that we should have all of these indices actually lie in the SUN and not lie in the U1. But we can use the U1 to get an identity. So for example, let's choose AN to lie in the U1. So it would correspond to a matrix that's proportional to the identity matrix. And then we collect all the terms that are proportional to TA1 through TAN minus 1, because the nth guy is just the identity matrix. And of course, that we know that that amplitude has to vanish because the U1 is inert. So that tells us that we have something equal to 0. It's the coefficient of each trace independently. And that thing is going to be a sum over the different positions in which you can insert the nth leg. So we'll have 1 through n minus 2, and then n minus 1, and all the way up to an 1, n 2, and then through n minus 1. And this is, in some sense, the simplest identity which these color-ordered amplitudes satisfy. And it's called the photon decoupling identity. And you can think of it as a special case of the Kleist-Keif identities, which I believe you already talked about? Yes. And that's actually still at higher loops kind of an open subject that to really understand in detail the identities of these color-ordered amplitudes, there are some that have constant coefficients, and those are the color identities, and then there's other class of identities which I guess you probably haven't talked about yet, but which you will see in Henrik's lectures, where you have non-trivial coefficients multiplied by the amplitudes. And then there are echoes of this at higher loops, and in fact even some exotic ones at tree level, which are still being understood in detail, and which I think neither of us will probably have time to talk about. So, as I mentioned in yesterday's lecture, one of the key ideas in scattering amplitudes is to use general properties of the amplitudes and turn them into tools for doing calculations. And at tree level, that tool is the principle of factorization. Now, at some point or other, I'm sure you've seen it all in your quantum field theory course, but I'm going to take a few minutes to review it here just so we're all on the same page. And so the basic idea is that in a consistent quantum field theory, amplitudes have to factorize when a sum of momenta correspond to some on-shell state. And the idea is that on-shell state can propagate over a very long distance, and so the interactions that kind of form that on-shell state have to be independent of the interactions that then take that on-shell state and turn it into the final state. Now, there are a few subtleties in Yang-Mills, which you probably have not seen in your quantum field theory course. Some of them at tree level and some of them at loop level. So the ones at tree level we'll talk about in a little while, and the others, the loop level ones, you'll have to discover on your own in some other context. So, for example, if we have some of external momenta approaching let's say, the mass of some particle, let's say 2, then we're going to have 2 particles approach some x particle, then, and we're looking at the amplitude for again, this by crossing is just going to be related to the amplitude 1 through n. I'm just, for the purposes of discussing factorization, I'm writing it in this form. So then we're going to get a left amplitude where we produce the on-shell state. It then propagates and then it decays to form our final state. Now, this is true beyond 2-particle states as well, even though we're not really used to the idea of scattering more than 2 particles to produce an intermediate state. If we were able to do that, the same ideas would hold. And so more generally, we can imagine that the sum of our different momenta approaches the mass of some on-shell state, and then we're going to get, again, a factorization of this Gedanken process into 2 different amplitudes. Which is producing the intermediate state, letting it propagate for a long distance. And of course, as we're getting closer and closer to the on-shell mass, the state can propagate further and further. And then finally, this intermediate state will decay into our final state. So this is kind of the general picture of factorization that you will have learned in your QFT course. We're interested in Yang-Mills theories, where, of course, at least in the pure theory, the mass is 0. And I'm going to stick to higher on the board. So if R is bigger than 3, then everything really works very straightforwardly. It follows this general pattern. So we can do this pictorially. I guess there's actually, there is some blue chalk. I don't know how visible that's going to be. Anyway, I'll draw it in white. So we imagine that we have, for example, 3 particles, and then we have some endpoint amplitude. And so we're interested in the limit that the sum of these momenta becomes null. But we have to do that in a special way so that SAB, SBC, and SAC do not go to 0. And actually, that's a good exercise. Find a configuration of momenta that have this property. This is within 3 momenta within some set of n momenta. So set them up with one parameter that satisfies these conditions. So this will factorize, in this case, to a 4-point amplitude. And so we have our particle x, and we have our propagation. I will typically omit the I epsilons, but you should always think of them being there. And then there's some higher point amplitude that takes the x into the remaining legs. So I'm missing one thing here. Does anyone see what I'm missing? I'm not going to make you come up to the board and put it in. Just raise your hand if you see what's missing. I'm sorry? Yes, exactly. So if there's multiple states that are degenerate, then of course you have to sum over the production of those states. And indeed, we do have multiple states that are degenerate because the gluons, intermediate gluons, can carry helicities. So, and again, the convention that I'm using is that the momenta are always outgoing, and when you flip the momentum, you also flip the helicity, and that's why the helicities match up in this way. The helicity, of course, is conserved along this line, but the notation is taking into account the fact that we're flipping the momentum. And more generally, of course, there's also going to be a sum. If we were doing this at the level of the full amplitude, then we would also need to sum over colors, because there's another, that's another degeneracy over here. Here I'm really thinking in terms of color-ordered amplitudes. Now, of course, we're not just interested in the case that R is bigger, 3 or bigger. We do have to consider the case that R is 2. And so here we're doing this with real momenta. And as we already saw, with real momenta, then the amplitude we would have on the left-hand side here would be a 3-point amplitude, and it would simply vanish. And so that simple factorization cannot work. On the other hand, if we combine it with the propagator, so this is going to 0 as you're approaching on shell, this is going as 1 over 0, then we get something which is essentially a 0 over 0. And whenever you see a 0 over 0, that's a sign that there's something that needs to be resolved. You need to put in some regulator, for example, and understand what the rate at which these things are going to 0. Do you get 0? Do you get something divergent? Do you get something finite? Now, we already know how to get something sensible out of this. And if we look at our earlier formula, then just count again the powers of energy. We had energy cubed in the numerator. Each spinor product goes as a power of the energy, and energy squared in the denominator. So we're getting something which is going to 0 linearly in the energy. On the other hand, the propagator is going to 0 as energy squared. So if we write these two objects together, the propagator denominator, then this thing, the combination of these two is roughly speaking going to go as 1 over the square root of an invariant. And these objects, this combination of objects, is something that's called a splitting amplitude. And they play a very important role in the analysis of collinear and soft limits of amplitudes, and in turn, they play a very important role in the construction and understanding of infrared divergences and the construction of counterterms for real emission contributions to differential cross-sections. That's not a subject that we're going to cover in these lectures, but it's something that if you do end up doing any of that, you'll have to learn, and this is kind of the amplitudes entry into that subject. And in fact, these at tree level, these things are related in a very simple way to the famous Altarelli-Parisi kernels. How many people have seen the Altarelli-Parisi kernels or heard of them? No, I mean, obviously, my goodness. How many people have heard of Guido Altarelli? Okay, how many people have heard of Giorgio Parisi? Okay, well, you should look up Altarelli-Parisi kernels, since they, even today, play a very important role in QCD physics at colliders. So that's what one has to do if one is thinking about real momenta, but mercifully, if one does actually think about complex momenta, so now we're thinking about amplitudes that are continued into the complex plane for the external momenta, then even in the r equals 2 case with complex momenta, everything works in more or less a straightforward way, because the propagator is indeed going to diverge, let's say, if we have two particles, 1 and 2, as S12 goes to 0, but that will happen either through the angle product going to 0 or the bracket product going to 0. And these will be two different limits. So, okay, so that's how factorization works, and there's a small subtlety with the 2-point factorizing 2 particles off. So how are we actually going to use this to calculate anything? So this is where the Brito-Cacciazzo-Feng or on-shell-Witten or on-shell recursion relations, usually abbreviated to BCFW, come in. And to look at them, we're going to introduce a complex parameter z, and we're going to take the spinors that are associated with our amplitude, that are which the amplitude is a function of, and we're going to shift them. So we're going to define an operation JL, and I always get confused myself as to which of the J or L are associated to which spinors, but the mnemonic is that it's the first one that's close to the bracket is where the bracket spinor is getting shifted, and the one that's close to the angle is where the angle spinor is getting shifted. So we're going to define a shift operation, and we're going to replace, actually let's make that a minus. We're going to replace the jth spinor with the jth spinor minus z times the lth bracket spinor, and for the L angle spinor, we're going to shift it by the opposite amount in z, but now times the jth angle spinner. So this in turn is going to induce a shift in the external momenta. And if you had started with real momenta, they're going to be, now they're going to be complex, but otherwise everything is left unchanged. So what happens to the momenta? So kj, for example, is going to now become a function of z. And that function is, of course, the original momentum. And we have a shift vector that is subtracted off. And likewise, for KL, it's going to become a function of z, and that function, again, involves a linear shift in the opposite direction by the same shift vector. Can anyone tell me why there's a factor of 1/2? Yes. Actually, can you speak up because I can't hear you? Yes. Yes, exactly. It's just when you recontract the sigma matrices to form a momentum, there's a factor of 2, which historically is known as the Gordon, as part of the Gordon identity. So we can look at these momenta, we can square them, and then we find, just doing the algebra, that we get 3 terms. And the last term, we can just use the Firt's identity to get z squared over 2 times the angle product of jj and the angle product of L and L. So, well, kj, of course, is an on-shell momentum, so that's 0. Here we have an angle product of j with itself, so that's 0. Here we have both an angle product of j with itself and L with itself, so that's 0. So in fact, even after the shift, the jth momentum stays on shell. And somewhat shorthand notation for this complicated object is going to be hatting it. So this thing I will denote, and in fact, I think the literature mostly denotes it as j hat. And of course, the same thing is going to be true for KL. So KL squared is again going to be 0. So again, we still have an on-shell scattering amplitude. And we can also observe that it's exactly the same shift vector, but with opposite signs. So if we look at the sum of these two momenta, that sum is unchanged. Now, the other spinners we're not modifying. So in fact, the momentum conservation is unaltered, so we still have an on-shell scattering amplitude just now with complex momenta. But of course, as we've seen at the level of 3-point amplitudes, that's not at all disturbing. So we now have a continuation of our amplitude in the complex plane. So of course, the shift of the spinners and the momenta is linear, but in general, the amplitude is some complicated rational function, and so there'll be shifts both in the numerator and denominator, and a priori for any given amplitude, you don't know what that shift is going to look like ahead of time. So we're going to make an assumption which you can justify using a Gedanken calculation in Feynman diagrams, but I'm not going to go through that argument here. We're going to assume that as we take z to infinity, that this shifted amplitude goes to 0. And in some special cases, you can actually relax this assumption, but I'm not going to discuss that. So what we want to do is consider a contour integral. So we're going to consider, this is the z plane, and we can imagine that there might be a bunch of poles out in the plane. We're going to consider a special integral. So of course we're going to divide out by 1/2 pi I, just so that we get something sensible at the end. So it's not going to be just the integral of a of z. We're also going to divide by z. So we know that there's going to be a pole at the origin. And then in general, a of z is some rational function of z, so it can have poles scattered elsewhere in the complex plane. So we're going to take a contour here that is the circle at infinity. It's a very big circle. Now, along that circle, dz over z is just going to reduce to a radial integral, but a of r is by assumption going to 0, so this integral is actually going to equal 0. So at first glance, that may not seem very useful, but we can use the knowledge of that 0 to extract some very useful information. Are there any questions about the setup at this point? Okay. So we have an integral that we know is 0, but we also know how to evaluate a contour integral. And we can evaluate it by taking residues. So to do that, we need to know where are the poles. Well, one pole, we already see explicitly where it is. There's a pole at z equals 0. And if we evaluate the residue there, then, or evaluate the integral, we're just going to get 2 pi I times the residue. That cancels the 2 pi I in front. And so the residue at z equals 0 is just going to be a of 0, which is just our original amplitude. So this overall 0 now turns into a useful equation if we can evaluate those other residues, because we just get a sum over all the other poles other than 0 of the residue at that pole of a of z over z. So where do the other poles come from? And from the earlier introduction, you can guess that in fact the answer is factorization. So let's imagine that we have some sum of momenta let's say K1 through KR. So generically, if we've just chosen non-special values of the various momenta, this thing is not going to be equal to 0. But, and that's going to be the case if all these momenta are Z independent. But now let's suppose that J, but not L, is one of these momenta, and that KL is not in that set. So now, as Z wanders all over the complex plane, in fact, this object is now guaranteed to vanish somewhere. And when it vanishes, then we have exactly the situation that was envisioned in the factorization. We have some sum of external momenta lying exactly on the mass of a physical state, here 0, because the physical states are all massless. And in fact, we're not just approaching that pole, we're actually sitting right on top of it. So, and of course, the same is going to be true if, by momentum conservation, if I were to exchange the role of J and L. So if J were not a member of this set, but L was, then again, we would be getting somewhere in the complex plane, we would be getting a pole. So let's introduce just a little bit more notation, just something to avoid writing out. So a sum of momenta from I through R, I'll just denote with I through R indices on a capital K. I hope my capital and small k's are distinguishable from each other. So of course, this undergoes a shift when we perform our shift transformation, and we can write out that object. So that thing is, of course, the original sum of momentum. And it's just shifted by the shift vector. And here I'm assuming the case where J is a member of this set, but L is not. If it were the other way around, the sign would be the opposite. Yes? Do we have a guarantee that there are simple poles? The answer is yes, we do. Why? So here I can give you an argument from Gedanken calculation from Feynman diagrams that you do not get any propagators that are 1 over a denominator squared. It's not an object that you can get. So the sum of so you know that the rational function is equivalent to the one that's given by Feynman diagrams, and so it has to be, for example, it has to be linear in each of the polarization vectors of the external gluons, and it has to have only simple poles. So if we square this thing, then of course the quadratic term in Z, which you might worry is going to disturb my confidence that there's always a solution somewhere, actually vanishes because it's the same as for the shift of just a single momentum. And so the square of this object as a function of Z is just going to be the naive square, and then there's going to be a linear shift term. And of course, we can see exactly when this vanishes. It vanishes when, I'm just going to label the Z rather than by A, by the 2 outside momenta of the set, when this object vanishes, and if we solve that explicitly, we just get this ratio. Okay, so this indeed corresponds to a factorization in this capital K squared as a function of z channel. And as I've already said, it's an exact factorization. We're actually sitting directly on the pole. And this is a factorization of A of z, so of our analytically continued amplitude. And it's a special kind of factorization because J is sitting in one set of momentum, so it's sitting, for example, in the left amplitude, and L is sitting in the right, or vice versa. So we can write out what that's going to look out pictorially. I think that's a good way to see that. So we have J hat here, and now we have 1 over K squared as a function of z. And if we were just trying to evaluate it numerically there, we'd be in trouble because it is actually infinite, but we're trying to take a residue, and so we do want to be sitting arbitrarily close to the pole. So what does that mean? It means that our sum over poles other than 0 is going to correspond to whoops. Let me try to write that more carefully. It's going to correspond to a sum over partitions of the external legs such that the two shifted legs are one is in the partition and the other is in the complement of the set that is removed. All right, so what is the residue? So we're looking at the residue of some function divided by z times k squared of I. Actually, this should be an I. I've been writing 1 here, but I really should have been writing an I. Let me fix that. Apologies. Should always be an I here. This is an I. So this is ki through r of z. And the z here is just the extra factor of z that we put into the integrand. And you'll see in a couple minutes why we did that, other than, of course, guaranteeing that the integral will converge. So we know what the factorization looks like. We get a left amplitude and a right amplitude, a left amplitude and a right amplitude. So we're going to take the residue of that object. There's an I for the propagator and the right amplitude. And then I'm just going to rewrite this in terms of ZIR. And we have a minus sign here because it's on the right-hand side of the equation. KI through RL. And okay. So it's a simple pole, and so we're just going to evaluate essentially the coefficient of that on the pole. So we multiply by the pole and then take the limit. So we're going to get AL evaluated at ZIR times AR, again evaluated at the location of the pole, and we have a factor of the location of the pole, and then we're multiplying it by this spinner product. Well, so we see what the ZIR here, if we multiply by this spinner product, it's actually just going to cancel the denominator. And what we're left with is just the product of the two sub-amplitudes. And we divide by what we might have thought is the naive pole in that channel. So if we didn't know anything about the shifting and the residues and all that sort of stuff, and then we just look at the sum of momenta here, they're going from I to R, and if we were to write down the naive denominator that we would have here, it's exactly K IR squared without the shift. So we can now put all of these pieces together. So our color-ordered amplitude is just a 0, of course, and that is going to equal the sum over partitions of one. Let me just write it as partitions P. And we also have to sum over the helicities of the intermediate legs. So we have the amplitude on one side, which has to have the J shifted leg. And then there's going to be, again, the shift on the common momentum. There's the naive pole. So here, P is really denoting a set of indices. It's a set of consecutive indices because everything is ordered. But I'm also identifying some set of indices with the momentum, the sum of momenta over that set of indices in the same way that I'm identifying indices with momenta. And that's going to be multiplied by an amplitude for the remaining indices. And here, the Lth leg has to appear. And again, the hat here means it's evaluated at the location of the particular pole, ZIR, that corresponds to this partition. And here we have, of course, the other. So let me actually just emphasize that this is all evaluated at the pole. So the partitions here are partitions such that J is in the partition and L is not in the partition. And of course, the complement of the partition is just the full set of legs, removing the legs that are in the set P. Now, of course, we have to have a non-trivial amplitude, so the number of legs in P has to be bigger than or equal to 2, and likewise, we also have to constrain the number in the complement to be bigger than or equal to 2. Now the P here corresponds to the external legs, and P bar corresponds to the external legs here, but we also have to allow for the internal line, so that's why there's a +1 over here and over here. So because of these constraints, then the number of legs here and also here is smaller than n. So these are now simpler objects. We've taken some endpoint amplitude and written it in terms of a sum of smaller amplitudes. And there are a number of comments that I should make. But before I do that, I'll stop and ask, are there any questions? Yes? No, this is a tree-level result. So the other place that you can make use of it is if you have a rational function. So for example, there can be rational functions, rational contributions at higher loops. And if you know the factorization of those rational functions, then you can apply this machinery. So the key here, it doesn't, of course, have to be the same factorization that would be true for a tree-level amplitude, but it has to be some known behavior. And then you can derive an analog of these results. But these results do depend on the fact that A of z is a rational function, and so that means that when you're wandering around in the complex plane, you only need to worry about poles. You don't need to worry about branch cuts or discontinuities and other more exotic kind of objects that can arise. So I think at the end of tomorrow's lecture, or maybe depending on how slowly I go, sometime on Thursday's lecture, then you'll understand how this fits into the picture of computing loop amplitudes and how you can apply some of this. So it would take me a little bit too far afield to answer that. There was another question somewhere? Yes? You don't need spinor helicity to talk about factorization. Yes. Yes. So in fact, you could do the shift, not referring to spinors, but using momenta, and you could run all of this machinery in the same way. I think pedagogically it's much more complicated to show that, and it also is uglier in practice, but it can be done. The key point here is that you have factorization, you need complex momenta, and the fact that tree-level amplitudes are rational functions. Those are really the key ingredients. So the numerator that corresponds to the projector here, no, that's actually absorbed into the amplitudes. And that would be true for gravity. It's essentially a helicity projector and a helicity sum, and that is actually absorbed into the amplitudes. The numerator has to factor in the on-shell limit, yeah. And I think that is essentially going to be true in any consistent quantum field theory. Okay, so let me make a few comments. So we have a recursion relation, and it eventually will terminate when we reach A3. And there's nothing else, at least in pure Yang-Mills. So again, if you imagine that there's some extended theory with higher dimension operators corresponding to new amplitudes, new basic amplitudes, of course, those would terminate. But in pure Yang-Mills, it's just A3. And so I think there was some question yesterday, I forget from whom. The point is that A4, the 4-point amplitude, is not an independent object. It's also built the same way at a 3-point amplitude. So the fact that there's a 4-point vertex in the Feynman rules in Yang-Mills, from this point of view, that's a red herring, and really its role there is to kind of fix up the gauge non-invariance if you were to try and run some of these ideas off shell. So the number of terms that you get at any given step is something like L minus J times n minus 3. And so if you're actually using this in practice to do analytic computations, then it's best to choose L and J relatively close together, and that's going to limit the size of the sums over partitions. It's going to reduce the number of partitions. And again, something I'm not going to discuss in these lectures, but of course, the choice of L and J is, there are certain restrictions that we're going to go through in a few minutes, but there's a wide variety of choices, and they all will give rise to the same scattering amplitude, and that reflects certain identities in the complex plane, and you can also map it into identities in the language of Grassmannian. So this is kind of one of the portals to start learning about the amplitudehedron and Grassmannians and things like that, and relations between different presentations, different decompositions, different BCFW decompositions of the same amplitude. There is actually some insight you can gain by looking at that. We're not going to do that. Okay, so I haven't actually said anything about, I've said that there's many choices of J and L, but which choices are legitimate, and you can actually do, again, it's kind of an example of the role of doing Gedanken calculations in Feynman diagrams. You can make a general argument on diagrammatics without ever actually writing down a single diagram, but I think pedagogically it's easier to go back to the MHV, the Park-Taylor amplitude, and write it down and just play around and understand what kinds of shifts are legitimate and which aren't. So I'll try to leave this formula up on the board so you can refer to it as I'm going through the different cases. And then so we're going to do shifts on here just to get a feel for what's going on. And of course, it's just an example. In fact, it's a very special amplitude, so we can't prove any general rules from it. In fact, strictly speaking, I've just pulled this amplitude from the literature, from thin air, as any of you might be concerned. And so we haven't actually computed it yet. So there's a little bit of a chicken and egg problem, and the Feynman diagrammatic argument would be a way around that. But again, I'm going to focus my time on other things. So let's start by taking M1 to be 1 and M2 to be 4, and let's just do a bunch of shifts. So one thing that's very special about this amplitude is that only the angle spinners appear here, so we don't actually have to worry about the bracket spinners. And so let's look at case 1. out of, let's see, how many am I actually going to go through? Well, there's 6. I don't know if I'm going to go through all 6. So let's look at, so 1 is a minus and 2 is a plus. So this is a nearest neighbor. This is a nearest neighbor minus plus shift. So here we're going to shift angle 2, and we're going to shift it by something that is proportional to the angle 1 spinner. But because the 1 with 1, the angle product of 1 with 1 vanishes, the 1-2 spinner product is actually invariant. The only one that shifts is the 2-3 product, which will shift by something linear in Z. And so there's just one linear term in Z in the denominator. So as we take Z to infinity, of course, the constant term will become irrelevant. And so then A, the amplitude, will go as 1 over Z as Z goes to infinity. So this shift would be a good shift if this property were true more generally. Because all we need is for A of Z to go to 0 as Z goes to infinity. So let's look at another case, which is 1 minus 3 plus. So this is a non-nearest neighbor minus plus shift, excuse me. And now we have still the angle 3 is the only spinner that's getting shifted. So that's not any different. But we now have 2 spinner products that end up getting shifted. So the 2-3 product is going to get shifted, and likewise the 3-4 product will get shifted. So now there are going to be 2 factors which are linear in the denominator, and again the constant terms become irrelevant as Z goes to infinity. So we get 1 over Z squared as Z goes to infinity. Case 3 will be a nearest neighbor plus plus shift. And it's the same spinner that's getting shifted, although by a different amount. And again, here, because of the nearest neighbor, the 2-3 is not going to get shifted, because instead of 1 here, we'd have a 2. But 3-4 will get shifted in the same way as over here, although instead of a 1-4, it'll be a 2-4. So again, we'll have one linear factor in the denominator, and we'll have A going as 1 over Z as Z goes to infinity. So far, all of these shifts are looking good. But if we look at case 4, so now let's do a, actually let's skip ahead to case 5. Well, now let's do case 4. So it's a nearest neighbor minus minus shift. And of course, you might think that it's going to be very similar to the plus plus, but on the other hand, the amplitude is, this particular amplitude is asymmetric, so maybe not. Here we're going to shift the spinner 4. But 1, 4 doesn't shift because, again, 1, 1 is vanishes, so that one stays invariant. So the numerator, which is 1, 4 to the 4th, stays invariant. And here we do get 2 spinner products that are shifted. I think at this point you can probably write down the shifts yourself. So again, A is going to go as 1 over z squared as z goes to infinity. Let's try a different case, which is a nearest neighbor, but now a minus plus shift. Sorry, plus minus shift. If anyone is watching the video, they're going to get very confused. And here we can see that something different is going to happen because now the numerator is going to be affected. So angle 1 is going to angle 1 plus z of 2. And now 1, 4 is going to be shifted. And of course, that is, with our choice of M1 and M2, that is what the numerator is. So we have the 1, 4 to the 4th in the numerator. There is going to be, again, the 1, 2 will sorry, 1, 2 here will not be shifted. But N1 will have a non-trivial shift. So it'll be proportional to z times the angle product of n and 2. So here we're going to get 4 powers in the numerator and 1 power in the denominator. So here we actually have a bad shift. So for the plus minus case, then as a goes to infinity over here, a will actually go as z cubed as z goes to infinity. So here, this violates the assumption that we would have made. And the final case is a non-nearest neighbor plus minus shift, and there, again, you get a goes as z squared, so again, it's a bad shift. Now, the results that we've worked out here are special to the Park-Taylor amplitude, but it turns out that these patterns really do hold more generally. So more generally, the minus plus, the plus plus, and the minus minus shifts are legitimate. And the plus minus shift is bad. And the other feature that holds more generally is that non-nearest neighbor shifts have better power behavior. But of course, you have the penalty of, if you were to use them, of having more terms in your BCFW equation, and you don't actually need, for the BCFW equation itself, you don't actually need this extra better power shift. The better power shift does allow you to derive what are known as bonus relations, and maybe Henrik will talk about them. Are you going to talk about them? I'm sorry, yes, that's right. No, but it's a different way of proving the results. So anyway, there are useful things you can do with these non-nearest neighbor shifts, but you don't need them for the basic BCFW results. So I'm going to run a little bit over and do one example. So let's do a simple example. Which is to compute a 4-point amplitude. So we're going to pick a 2-3 shift. So it's a minus plus shift. And we can write it out. So we're going to shift the bracket product, the bracket spinner 2 by something that is proportional to the bracket spinner 3. And we're going to shift the angle spinner 3 by something that is proportional to the angle spinner 2. And all the other spinners are going to be unchanged, and that includes the angle 2 and the bracket 3. So some of the hats that show up in the diagram might actually mean doing nothing. So let's see here. Let me draw it up here. So these are neighboring shifts, and there's actually only one partition that we can make of 1, 2, 3, 4. That's, of course, also reflects the fact that we're at very low multiplicity in perturbation theory. So let's first, we're going to have the naive pole, which is just S34. And so we're going to have a p hat minus directed this way and minus p hat plus directed this way. So the first observation is that here we of course do have a sum over helicities, but here that sum over helicities reduces to just one term. And the reason is that if we were to choose a negative helicity here, then we would have a minus, minus, minus amplitude, and we've already seen that that object is truly 0, even with complex momenta. So we only have one term. And of course, once we fix this one to be a plus, this one has to be a minus, although, in fact, if it had been a plus, then this amplitude would also have vanished independently. But in general, you only need to worry about one side, the helicity argument on one side of a factorization. So let's just start writing this out. So these are two 3-point amplitudes. We have the formulas for those. We just have to be a little bit careful about the minus sign. And so, of course, we have 1, 2 cubed. And then we just write down minus p hat and then minus p hat 1. So that's on one side. And then we have I over S34. And then, in fact, I didn't explain that, but it turns out the constant for the plus plus minus is actually minus I. And now we have, again, p hat 3 and 4 p hat. So I've just written out for the actual momenta here the expressions that we derived yesterday for the 3-point amplitudes. So one has to be a little bit careful if these are attached to fermions, because one has to worry about the direction of kind of charge flow. But in this case, we can take the negative spinners we can just pull out the factor of minus. It turns into an I in front. In general, one has some freedom in deciding where to assign that phase, whether to the angle spinner or the bracket spinner. But here I'm going to do that way. And now we want to, having then removed the minus sign from inside the spinner products, we want to link these up, because then we can use the Fierce identity. And there's 2 ways really of doing that. We could imagine linking this P to the first spinner product or to the second one. And it's going to be just, the algebra will be a little bit easier if we do it this way, but I encourage you afterwards to do it the other way and see that you get the same result. So we can now write down our expression. So we have a bracket 3, 4 here cubed. We can cancel one of those powers against the S34, leaving just an angle product. And overall, we have minus I. We have the angle 1, 2 cubed. And again, the bracket 3, 4 squared. We have a 4, 3. And then combining these 2 strings together, we get 1 p hat 3 and 2 p hat 4. Now, what is p hat? Well, p hat is just given by the naive. Let me put in the indices here. It's given by the naive p, so just the sum of K3 and K4, or I should say actually sum of K1 and K2, sorry. But we have to subtract off the shift contribution, and that's proportional to the shift vector to mu3, because we shifted one by angle 2 and the other by bracket 3. That gives us the shift vector out of contracting those 2 spinners. And so P here is going to be just K1 plus K2. And that's, of course, by momentum conservation. You could also write it as minus K3 plus K4. And so if we work out, for example, 1 p hat 3, then that thing is just there's the p term, and then there's the shift term. And that thing is 1 mu3 times 2 mu3. And you can see that when we use the Fierce identity here, we're going to get a bracket product of 3 with itself. So this term is actually just going to vanish. And the same thing is going to be true for the other product in the denominator. We're just going to get 2 p4 minus z12 over 2. And then again, there's a 2 mu4 contracted with our shift vector, which is angle 2 mu bracket 3. And here, it's the angle product, which when we use the Fiertz identity, which is going to make this thing 0. So this thing, when the dust settles, of course, we can, it's actually more convenient to write it using K3 plus K4. And of course, the K3 term is going to vanish. We're just going to get, it's going to just decompose into a product of spinners. So and the second one is just going to give us, again, minus 2, 3 times bracket 3, 4. So we have 2 powers of the bracket product of 3 and 4. We have 2 of them in the denominator, so we're going to be left with none. And the other terms we have are, again, their nearest neighbor, and nearest neighbor. And of course, there's no 4 because the 1, 2 has canceled. So what we're left with is just plus I times 1, 2, the angle 1, 2 cubed, and then 2, 3, 3, 4, 4, 1. And of course, you'll recognize this is exactly the 4-point case of the Park-Taylor formula. So this, not only does the formula generalize, but the calculation generalizes as well. And so that gives us another exercise, which is prove or derive the formula for the Park-Taylor amplitude. So the Park-Taylor amplitude is called maximally helicity violating because it corresponds to the tree-level amplitude that has the maximal violation of helicity. And I think I already mentioned this, but there are 2 amplitudes that would, in principle, have more helicity violation, where they're all plus or you have 1 negative helicity. And of course, they're complex conjugates where they're all negative or all but 1 are negative. And these amplitudes vanish. That can be understood by supersymmetry, but, and I should mention, it should be obvious, but you should do this by induction, of course. And the other exercise that you can go through is to derive or to prove these results. Using BCFW. And finally, one last suggested exercise to really check that you've understood things is to compute a 6-point amplitude. And it's a specific one where all the, which is split, so there are 3 negatives and 3 positives. And this, in a sense, is the first amplitude, the simplest amplitude, where you'll see a multi-particle pole. And it has actually quite a simple form, and you can check that in the old review article by Mangano and Park to see if you've gotten the right answer. So with that, let me stop today's lecture and ask if there are any other questions.
Okay, we have time for 1 or 2 quick questions. If people are not too hungry. Oh,
yes.
there, okay. Wait for the microphone, please.
You said the shifts keep being good or bad if you go out of the Park-Taylor formula, but I feel like for example, in this A6, you're going to have the same row for minus and plus elicities. So I don't see.
I didn't prove that this pattern is are legitimate. So when I say they're a good shift, I mean that the amplitude has a scaling behavior as z goes to infinity that allows you to use that shift for the BCFW. When the shift is bad, then it corresponds to one of these shifts where the amplitude is actually growing, so you cannot use that shift for the BCFW. And of course, we only saw this by looking at the example of the Park-Taylor amplitude, but it turns out that those patterns do hold more generally, and you can actually prove that.
But for example, for this A6 with 3 minus, 3 plus,
Yes.
here you're saying the minus plus is good and plus minus
The same
bad.
thing will be true.
But it seems symmetric.
It doesn't matter.
It doesn't matter.
Doesn't matter. And actually, once you derive the formula, then you can try out the explicit bad shift and see what happens.
Okay, thanks.
Also a good exercise.
Any other questions?
Yeah, the bad ones are the ones that shift the lambda tildes that have plus signature. So that means that there is lambda
Right.
tildes
Right.
upstairs. That's why they are bad.
That's right.
That's why it's not symmetric.
That's right. Yeah, it's I should have maybe explained that the symmetry comes from the question of whether the helicity, the plus helicity is attached to the bracket spinner or to the angle spinner. So in fact, it's not symmetric. Yeah.
Oh, maybe I just have one comment. Someone may ask, well, why don't we do Feynman diagrams in this 4-point example, right? Because you only seem to have like 1 or 2 terms. In this case, yes, you have one term. If you do auto shifts, you may have 2 as well. But I think the nice thing about BCFW is, at higher points you can see like Park-Taylor only from 1 term, and that is the fact that most of the terms that you would expect naively, you would expect these n-3 terms, but I think they cancel. Like you don't have the helicities to make them work. So Park-Taylor is only 1 term. It's always on 1 term, I think, right?
I mean, it's only 1 term by which method of calculation?
By any
Yes,
shift, but yeah.
Yeah, you can set. I mean, you can set it
Yeah.
up in such a way that it's 1 term. That's
Yeah,
right.
one.
No, I mean it's actually a good exercise to work through the 4-point amplitude from Feynman diagrams, and then you can see how the terms combine. And yes, that is a simple enough exercise that with the Chinese magic spinner. Chinese magic polarization form, it's relatively straightforward to do it. But if you were to start to do the 5-point amplitude that way, then I think you would very quickly see how much simpler the BCFW is.
Any other question or comment? If not, let's thank David again.